Thank you so much for the introduction. Well, as you might know, this presentation was first presented on ICOM-CC in May of this year. But I'm very happy to share it with you today, also on behalf of all my co-authors who are listed here. I'll start by briefly introducing Jan Steen. Many of you will know him, of course. He's a Dutch 17th century artist, most famous for his genre paintings, even though he also painted portraits and history paintings. He was very, very active, and currently there are over 400 paintings that have been attributed to him. He often included self-portraits in his work. As you can see here, you can see him teaching a little boy to smoke, so setting a very good example. Steen painted both so-called high-life genre scenes and low-life genre scenes. The high-life genre scenes depict the daily life of rich people in lavish surroundings, and the low-life genre scenes depict peasants in their homes or in their taverns, merrymaking, as you can see here in these two examples. We've been carrying out research into Steen's painting technique and his use of materials since 2012. The Mauritshuis owns 15 paintings by Jan Steen, and these 15 formed the starting point of our research. These paintings cover his entire career, from his early start in Den Haag to the end, and they also represent all the genres Steen painted. Next to our own 15 paintings, 35 paintings from other collections were analyzed, and the goal of our research project was to understand the chronology of his work better, since he only dated around 10% of his paintings. During his career, Jan Steen lived and worked in several cities in the Netherlands. He started working in The Hague together with his father-in-law, Jan van Gooyen. And from this, he briefly moved to Delft, then to Warmond, and then to Haarlem. And he ended his career in his birthtown, Leiden. Our hope for this project was that there would be differences in materials between the different cities he worked in, and so that we could identify, or so that it would be possible to place certain paintings in certain cities based on the materials that were used. This turned out to be quite true for the ground layers, and our results of this ground layer research has been published in these two articles you see here. But today I will focus more on Jan Steen's green and blue pigments. So how did we do our analysis? We used a variety of analytical techniques to analyze the paintings, aiming to understand the layer buildup and the materials used by the artist. Apart from several non-invasive and imaging techniques, we analyzed minute paint samples from green and blue areas in 37 paintings. So, as I said before, Steen painted over 400 paintings, and only 10% of these are dated. We had the possibility to research 18 of these dated paintings, or of these paintings that were either dated by the artist himself or that could be dated because they depict a certain town very clearly. And these dated paintings represent his entire career. So we had early paintings from Den Haag and very late paintings from Leiden. The idea was that these dated paintings would serve as a framework for the undated paintings. Pigments were identified in cross-sections, first by looking at the cross-sections under the microscope, in visible reflected light and ultraviolet fluorescence to identify the color, size, and shape of the pigment particles. But subsequently, we used scanning electron backscattered images for particle morphology, and then we obtained elemental information by carrying out SEM-EDX, point measurements, and SEM-EDX mappings of the entire sample surface. So, what pigments did Jan Steen use? We actually encountered all blue pigments that were available in the 17th century in his paintings. So we found ultramarine, azurite, blue verditer, smalt, indigo, and even a little bit of vivianite. So I'll now discuss the pigments found per type of material depicted, and I'll start with blue clothing and draperies. And for blue clothing and draperies, he most often used ultramarine, azurite, verditer, and indigo. So Steen often used ultramarine in his work, and ultramarine was the most expensive blue pigment available in the 17th century, and it's made from the precious stone lapis lazuli. Ultramarine mainly consists of lazurite, which is the blue mineral, which is a complex sulfur-containing sodium aluminum silicate. But with the process of extracting lazurite from the stone, other silicate minerals are also released. And the particle size of lazurite and the ratio between the lazurite and these accessory minerals, oh, sorry, it's going a bit fast. The particle size of the lazurite and the ratio between lazurite and accessory minerals is a grade for the quality of the ultramarine. So the higher the content of lazurite, the bluer the pigment is. Because ultramarine was so expensive, it is mostly associated with high life genre painting. However, we also frequently found ultramarine in low life genre paintings, like this one, A Pig Belongs in the Sty, from the collection of the Mauritshuis. Here, the blue cap of the little boy is painted with low quality ultramarine, consisting of very small blue particles of lazurite and many accessory minerals. This lower quality of ultramarine is also known as ultramarine ash. For his high life genre paintings, Steen surprisingly used a similar low quality ultramarine. This can be seen here in a sample from the tablecloth of this really pretty nice little fine painting, a girl eating oysters from the Mauritshuis. Apart from small blue lazurite particles, which you can clearly see in the UV image here, many accessory minerals are present, such as the magnesium-containing mineral diopside. Another pigment stain used for clothing and draperies is indigo. And we found a specific type of indigo that emits a very strong, remarkable fluorescence under UV radiation. We noticed this fluorescence during the restoration treatment of this painting, The Mocking of Samson, which was treated by my colleague Sabrina Meloni. And it's from the collection of the Royal Museum of Fine Arts in Antwerp. And here you see a sample from these indigo containing paint layers. After SEM analysis, it became clear that the indigo particles contain aluminum, sulfur, and potassium. And this made us conclude that the indigo was precipitated on an alum substrate. This is not necessary for indigo. It's not necessary to precipitate it onto a substrate to turn it into a pigment. However, the Mayerne writes that this special treatment makes the indigo more stable. And we now assume that this treatment or this substrate is what causes the strong fluorescence, which is comparable to red and yellow lakes, also on an alum substrate. We have found this type of indigo in more 17th century examples recently. For blue skies, Thanes typically used smalt mixed with lead white. Smalt was a cheap blue pigment produced in large quantities in the Netherlands in the 17th century. It's made of ground blue cobalt containing potash glass. An exception are the commissioned paintings, like this portrait from the Rijksmuseum. Here in this portrait, in this cross-section you can see here, Steen mixed in some ultramarine into the smalt layer. And in this elemental mapping of a cross-section from the sky, we see blue smalt particles consisting of silicium, cobalt, and nickel. And those particles, are circled in blue. And then we have lazurite particles consisting of sodium, aluminum, and silicium, which are circled in red. As part of the larger Jan Steen research project, we have analyzed smalt samples of 21 of his paintings using SEM-EDX. To make smalt, silicium was heated together with a cobalt ore and potash. additional minerals present in the pigment, like bismuth or arsenic, can be assigned to the origin of the cobalt ore, but also to the production process. So different batches of smalt show a different ratio of trace elements. By quantifying the amount of trace element present in the smalt samples and performing multivariate data analysis on this resulting data set, we were able to distinguish batches of smalt and link them to the city Steen worked in. The results of this study have been presented on AIC 2 years ago, or 3 years ago by now, and these results will be published elsewhere. Now onto the green paints. There were not many green pigments available in the 17th century. There were copper greens like verditer and malachite, or green earths. But artists often used mixtures of blue and yellow to create greens, which is also what Steen did quite often. In As the Old Sing, So Pipe the Young, Steen used a green copper containing pigment to paint the green jacket of the woman on the left. And this is actually quite an exception, because this is the only time we have found this green copper pigment. It consists of large angular particles that are made of copper, and we also detected quite an amount of chlorine in these pigment particles. Unfortunately, we weren't able to perform further analysis, so it's not quite clear to us what this pigment is. Foliage and soil were predominantly painted with complex mixtures of azurite or blue verditer, mixed with earth pigments, yellow lake, Latin yellow, smalt, vermilion, and black. And in the sample from the fortune teller that you can see here, the rounded particles of blue verditer can be easily recognized in the copper map. One exception to these complex mixtures for green paints was found again in a portrait. The portrait of baker Arend Oostwaard from the collection of the Rijksmuseum. Here Steen used a very clean mixture of high quality ultramarine, which is clearly recognizable by the big blue chunks of lazurite and a yellow lake. So again, in a commissioned portrait, we see that Steen uses a higher quality of pigments than in any other painting. Even though green earth wasn't commonly used as a main pigment for green paints in the 17th century, we found it very often in Steen's paintings from the second half of his career. Green earth consists of the minerals celadonite and glauconite and has been used since antiquity, often in wall paintings or as underlayers, for instance in skin tones. Steen used the green earth as a primary green pigment in foliage, but also for draperies and clothing. Green earth is also found in paintings by, for instance, Vermeer and Pieter de Hoog, but they seem to have used it for specific purposes, whereas Steen really uses it to paint anything that's green, it seems. The first time we found this green earth was 10 years ago, while restoring the Doctor's Visit, the painting you see here. Through losses, we could see a very intense green paint used in an underlying composition. SEM EDX analysis of a paint sample didn't show copper, but predominantly silicium, potassium, magnesium, and iron. And this suggested that it had to be a green earth, but a very intense green earth. So after this first sighting of green earth, we found it in 10 of the 37 paintings we analyzed for this study, and you can see all those paintings here. Remarkably, all the paintings date from the second half of Steen's career. In some cases, the pigment particles of this green earth were very, very large, as you can see here. This is a cross-section of the marriage of Tobias and Sarah from the Herzog Anton Ulrich Museum in Braunschweig. The mapping with SEM EDX shows that the big green pigment particle consists of silicium, magnesium, potassium, and iron. So where does this green earth come from? There are several sources for green earth, and in the 17th century, the most common source The most common sources, I should say, were Montebaldo in Italy, but also Bohemia and Cyprus. We made paintouts of several types of green earth, and visually the green earth from Cyprus is what comes closest to the paint surface of Jan Steen. The green earth from Cyprus is very intense in color and gives this beautiful dark green when bound in linseed oil. However, other than the optical properties, the type and ratio of minerals found in the pigment might be indicative of the geographical origin of the green earth. So, hoping to be able to say something more about this origin of the green earth, we were able to perform micro X-ray diffraction on a cross-section, and we tried to distinguish between the minerals glauconite and celadonite. The results, as you can see here, the analysis showed us that both glauconite and celadonite are present in this pigment, confirming that it was indeed green earth. However, the results were inconclusive regarding the ratio between these two minerals. So unfortunately, we're still not quite sure where the green earth comes from, or why it all of a sudden appears in Steen's palette. To conclude, Jan Steen used all blue and green pigments available in the 17th century. He used ultramarine quite often, both in high life and low life genre, but it was generally of a quite low quality. For commissioned portraits or commissioned paintings in general, he tended to use a higher quality of pigments, as we saw in the portraits that we analyzed. For the greens, he often used a very complex mixture with a lot of different pigments, and from the second half of his career, we find a lot of green earth. This research wouldn't have been possible without the help of many people who are listed here today. They gave us access to their Jan Steen paintings. And this research was a collaboration between the Mauritshuis and Shell Netherlands. Well, yeah, I would like to thank you all for your attention. But also, now that I have your attention, I would like to make a little advertisement for our new exhibition, which is opening today. It's called Facelifts and Makeovers, and it's focused on interesting case studies from our restoration studio from the past years. So if you have a chance, do come by and see it. So thank you very much.